idea. Good, how are you? Very good.
Hey, Jared, how are you?
Good.
So, what are we doing today?
Choosing a presentation.
Yes, we do. I hope this idea induces a lot of enthusiasm in you guys, and you are doing it by free will as a replacement of less pleasant academic activities. So I printed more than needed copies, so I will distribute one per each for your memories, and then one copy will go travel around and you will mention what is your first or second choices. And the plan is that we will do it in 3 meetings from now, because next 2 meetings will be cancelled. So next week is your second or third break per semester. No meetings because of the conference. That is.
You're going to SES?
Yes.
Is Svetlana as well?
But some of us in the class are traveling. So the lists here are long, and the reason for these presentations, in addition to make you happy and entertain you, is to open the horizons. We cannot cover everything in details, and if we do 6 presentations per hour, you cannot speak for longer than like 7 minutes with questions. And the amount of possible questions here is too long. It is not possible to provide everything in full detail. So you are free to squeeze or select whatever you like, and you can select one first or second choice. But some of the subjects mentioned in this list are yet developing areas of science, and some of the questions do not have direct answers. So it is more to show challenges and navigate towards possible ways to solve them. So some of them do not have immediate final answer. So let me mark one of those. So and please complete it eventually by the end of the today's meeting, and I will collect the one with the sign.
I get first choice.
Hmm?
I get first picks.
Well, you write choice 1, choice 2,
Yeah.
and do not please do not look even if something is blocked. We will reshuffle to make everyone happy. So that Diane doesn't feel himself so happy.
I'm sure whatever he chooses, I will not want. So.
Well, I already have a.
Final diagram, so
Yeah.
I have an idea what you guys will choose. I have only a little debate between Levi and Jabet. There are 2 subjects that are interchangeable, and it is an
Which one is-
intrigue for me.
Which one's that?
Uh-oh.
Well, let you choose, and then I will tell my what were my bets, what I was betting for.
Oh, I know what I'm doing.
See,
So which was your bet?
let Jabet feel, or let everyone feel, and then we will open the intrigue. Really?
What? Oh,
Can
my
we-
turn?
I guess so.
Well, I was late, so does anyone else want to show first?
Sure. Anyone that bet does.
That's fine. That's fine.
Okay. Yeah.
I think Brandon and I will have similar choices.
Okay, something went contrary to my expectations, but it is fine.
2, aren't I? Here, I have to decide on 2.
Huh?
I'm sorry, I have to think about 2.
Did you make, I don't know one?
Yeah. That's what I wanted. Do first choice.
What about qubits?
What was my second? That was your second as well, so I can't choose the same.
Why can't you? Then he gets to decide who is who. Right?
Javid and Sam, please do not worry if your dream subject is already marked by anyone. I will resolve conflicts.
Why do you want 5?
Because it's
You should change it to 2.
I have 2 as well.
You should change 2 to your first and 5 to the second.
Why?
Because then we don't have conflict.
He gets to decide then. And
But I think 2 is
I was
the
planning
second
to
one.
start delivering material, but I'm very intrigued to see.
I think the second
Two
one's my
choices.
second choice, but it's this the second. We have 5. I mean, I'd
But-
much prefer 5.
but he gets to decide. And I am assuming that he is gonna assume that you want 5 the
I
most.
do want 5.
So therefore, I reduced his deliberation for my subject, because if I choose 5 for my first, and my second is to make everyone have first and second choice of the topic, believe that you want 5, then therefore
Take it.
he will
I
probably
was gonna
make
choose
mine
the second.
too. But I don't know.
Well, that's a lot of people's too. Alright. Do it, K's and
I think he's already deciding.
No. I'm going to check
First, that's a first.
how many times I won and how many times I lost.
Wait, Javed didn't do anything.
Yeah, he did.
Oh, I see. That's the one.
Should have.
Oh boy, what they, Javed the same, we did the same.
It's gonna be a. His,
So no one choose number 6. Although I thought it will be one of the easiest, and either Javid or Levi will select it.
see, I don't do silver nano clusters, so that's.
But it doesn't matter which system. It's algebraic problem. Everyone, okay. So my guesses were that Levi first, Sam number 2, Aaron number 3, Diane number 4. So I won here. Brandon number 5, I won here, and Jabet number 6, I lost here.
So you won 2 out of 6.
Yeah. Okay. So there are 1, 2, 3, 4, 5 people want number 2.
I guess if 6 is the easiest, in your opinion, I guess I
It
can
is.
just flip to
Basically, they're the same.
2 and 6.
Yes.
Then why do we have redundants?
into
Because you have the same math for the different problems.
Oh. Okay. Well, then I guess I can be 6 if.
Is that your first choice?
No,
That's your first
I
choice,
know
right?
that you're gonna get Brendan and MR. I chose 2 to be my first, so then my second would have a higher probability of being able to choose. Because I'm assuming he'll give you NMR.
Wait, so you strategically chose the one I wanted?
And there is only one volunteer for number 1.
So Diane gets that one, right?
No, he wants.
Diane wants number 4 and number 1.
Oh, I see.
For number 4, his first choice, very good. No, it will be yours. But number 1 is, I would choose it for myself if I would be
Yeah,
president.
number 1 is really, it should be one of the easiest.
Since Jabit, what do you think about number 1? Okay, we'll discuss. So, like, number 1 is the most orphan subject. No one wants it. But
I don't know about the lens coming model.
huh?
I don't know about this model. I mean,
Well, I will provide
lens coming
materials.
model. So I have no idea.
Longitudinal should be the least amount of research.
Why can't I do?
Sure.
Does my logic not make sense? If I think that you're gonna choose him for 5, I should choose my second one so it has a higher probability of being chosen.
You're using same part of a brain which one typically uses to play mafia. Like this one will guess this.
Why can't I?
I'm very pleased to chat with you guys, and we can do it for a couple of hours, but probably I need to present something. Or at least to have our discussion in somewhat related to the course. So, what is our who we are? What is our goals? What are our plans?
You don't want to bother with me.
So we are looking on the time aspects of several phenomena, and before in this course we covered angular momentum, which will be now very well applicable to number 6.
Oh, I hate angular momentum.
No, you will see that the rest, it is the simplest example for angular momentum.
Oh, good.
Two systems, 1/2, which has a trivial solution, but then we just add dynamics, see how it changes with time. Then we covered time-independent perturbation theory showing how levels are splitting, and in application to nuclear magnetic resonance, it means that because of the nuclear magnetic momentum, levels are getting degeneracy is lifted, and it is lifted in different amounts for different atoms, for different states, based on even if the nuclear moment is the same, in chemical systems it is screened by magnetic field of electrons, magnetic polarization of electrons, and therefore we have different amounts of splitting, and it is used to recognize different chemicals. And then we covered time-dependent perturbation theory, showing what is going on if you look on a time aspect in 2 limits. Either time is too short or interaction Hamiltonian is too small, perturbative solution. And then our 4th chapter is when approximations for chapter 3 are not valid. If you have strong field, how things are changing in time. There are 2 challenges to our memory that we have formulated as a quiz last time, and I'm just lazy to offer you the same quiz once again. I will just do it on the board, because we cannot go forward until we recall the correct equations. And you may help me with your notes or with your reminders. So we will do a little review and write down the equations of motion for density metrics and for spin projections, because no analysis can be done further without this input. And today we will talk about the same things that we have discussed and practically practiced last night in the lab. About 2 experimental setups where one does see a provocative phenomenon, the shortening of the Bloch vector, which can be falsely treated as getting spin less than I think
Glitched out for a second.
Hmm?
I think it just glitched out for a second.
Yep, but then it looks like it came back. Well, at worst case scenario, it will be just not recorded. So when we were doing time-dependent phenomena, for simplest possible example, for do a system, one meeting before, 2 meetings before, we were always considering an isolated system. Isolated, that it is like one two-level system in the universe, whatever it is, a molecule or spin, and there is nothing around. Now we are coming to an idea that it is either surrounded by other like molecules, solvent, or there are several copies of the similar systems around. There are ensembles. And as a result of this objective physical reasons, we will have modifications to the equations and to the dynamics. One of the strange thing that I can provocatively announce is the shortening of the length of the Bloch vector. So there will be two phenomena, relaxation and dephasing, that cannot be described if we assume only a single isolated system. And as soon as we consider it more realistically, we will have two additional phenomena and two additional terms into the equations. And these phenomena are proclaimed, are illustrated, these effects, these mechanisms are proclaimed in two experimental observed phenomena. One is free induction decay. It will be very related to several questions by Diane. He was keeping challenging me and asking me about nuclear magnetic resonance and trying to establish connection between what we do in class and his experience with this experimental technique. So we'll talk more about free induction decay from experimental side, and then, if time allows, about the photon or spin echo phenomena. So, least pleasant time. A quiz from last meeting. Row 1, 1, 1, row 1, 2, row 2, 1, row 2, 2. Time derivative. So, the density matrix for isolated system is formulated this way, but for systems in a statistical ensemble, the definition is there are different definitions. And in the simplest case, the time evolution of the elements of density matrix is linear, and change in time of a given element is contributed by linear combination of present values of all other elements. So we were deriving these equations, and if we would have perfect memories, we will be able to reproduce this equation with closed eyes in the middle of the night. And if you do not, we can use memorization techniques and memorizing that there are offset terms that correspond to accumulation of phase and that work in absence of external field, and there are Rabi frequency terms that are launched when the system is perturbed by harmonic external perturbation, and there are zeros. So there are 2 zeros, no, 6 zeros, 2 phase accumulations, and how many?
16 minus 6 minus 2.
Equals?
8.
Good. So, which elements are affected by the phase accumulation? Diagonal or off diagonal?
Diagonal.
Huh?
Diagonal.
Just
Or
two of the diagonal elements that correspond
Wait. It is imaginary. If you do like y period equals I y. It means that solution will be imaginary. And you know that diagonal elements rho 1, 1 and rho 2, 2 are always real. It's just probabilities.
I think
Not the
Always.
okay. The other two diagonal elements.
Those two are off diagonal, and those are diagonal. Typically, the density matrix is written in this.
Well, in the matrix that you have, in that operator matrix, there will be
Yes,
diagonal.
yes.
On the diagonal.
This is correct. This is correct. But it is not just navigation through the matrix. The words diagonal and off diagonal are specific terms.
Yeah.
Diagonal when indices coincide, off diagonal when they do not coincide. So we are mentioning that equation of motion for the off diagonal elements is contributed by this phase accumulation. Plus I delta h bar minus I delta h bar. Zeros.
That's not where we put them last time.
last time we did 1, 1, 2, 2, 1, 2,
6,
2,
0,
1.
right?
Yes.
Oh, we switched the
Yeah.
I didn't have intentions to make the life more complicated. It's just, but okay.
You can't couple it itself.
Right.
For right, yeah.
You can't couple itself.
Very good. You are like 75% of success. 90% of success. Perfect. Thank you much. Thank you, Jordan. Now, my life is much easier. The remaining places are populated by I omega r over 2, 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 omega r over 2. But they should come with different signs. Yeah. Will you try to feel pluses and minuses? Like half of them should be with plus,
Yeah.
half of them should be with minus.
I think
This is a hard task. I wouldn't do it from the top of the head.
good. Well,
Minus.
row 1, 1, row 1, 2 should be positive. They should be negative. Should be positive, negative, negative, and they should be
Minus, minus. Yep. Perfect. So, I think now you guys are ready to take the quiz again. But we will not do it. But I'm confident that you are ready. So you can do it some other time if you have nothing else pleasant to do.
So that means never.
Who knows? If I will fail to prepare materials for the lecture, then you'll fill the time by a quiz. What else do we need as an introduction, as a starting point? If we are interested in the projections, we can combine by adding and subtracting elements of density matrix and getting the projections of this spin if it is NMR or quasi-spin if it is optics. And then density matrix elements can have complex values, especially off diagonal. But these projections are always real and they are related to actual observables. probably we should do same style as a matrix. So it will be linear combination Sx, Sy, is Z with different coefficients. So what can we remember from our last meeting? At least we can place some zeros. We can say which there should be 9 coefficients, and we know that some of them are zeros. For example, we do know that X projection doesn't depend on Z. We know that X projection doesn't depend on itself. We know that Y projection doesn't depend on itself. And we know that Z projection doesn't depend on itself. So the X and Y are cross conjugated, and we may just check what are the signs here in our last derivation. And there will be Rabi frequency coming for cross conjugation of the Y and Z projection. But we should check whether they come with equal or opposite signs.
So you have equation Sy is negative
Where?
for your
Here.
Sx equation, yeah, that'd be a negative.
Okay, yeah, thank you. Here is negative, then here it is plus. And for the second part,
Sy is negative for the bottom equation.
very good. Thank you. So we were able to derive it just by merging density matrix equation of motion with observables, with definitions of expectation values, and then get this equation. But if we suddenly need it, we can practice memory maybe again and again. So X and Y are conjugated by delta, and Y and Z are conjugated by Rabi frequency. This equation corresponds to explorer traveling on the surface of a globe with the radius h bar over 2. So the distance from center of the globe to the surface is Bloch vector, and it makes trajectories always staying on the surface, which is correct for the isolated system. As soon as we include two additional mechanisms, one that there are several similar replicas of such systems, ensemble, or that each system has its environment of other molecules, we will have additional terms in this equation. So the terms that we just recalled contribute to oscillatory solutions. They are cross-conjugated. From one element you get transform non-zero values to another element. And here they are diagonal, so time increment of Sx constantly decreases with the rate 1 over T2. Sy decreases as 1 over T2, and Sz decreases as 1 over T1. The rates are also referred to as longitudinal when in comparison to external constant magnetic field. Our Sz vector is parallel, is along the B vector. Therefore, this T1 is called longitudinal. Sx and Sy are orthogonal to the B vector, so they are transversal. Right now, we did, and if we introduce these additional terms into equation, it means that the length of the vector will change. It will decrease. Whatever we do, it will become shorter and shorter. From now on, our goal is to justify where to take these constants. How to rationalize the rates of this relaxation. Our major goal and our secondary goal is to establish a bridge to real experiment and see how these relaxational phenomena affect the observations.
Like Ti,
Not I. one.
yeah, but T1 and T2, are they always positive?
Yes. Their times. It's
Oh.
relaxation time and dephasing time. So how soon the system relaxes, how quickly the length of the vector shortens. So variables. Rationalize values of T1, T2, and bridge to experiment. So where we are in our plan. We are done with review on density metrics, on Bloch equation, on longitudinal and transversal. Before we go to mathematical aspects, let's talk qualitatively about NMR. And you are very welcome to contribute, especially if you have ever touched the apparatus, because I didn't. It's very new for me. So, suppose that we do have two types of spins with different splitting in a given magnetic field. Right? So spin 1 and spin 2, well, it is maybe not the best way, but to show that they will revolve with different frequencies, omega 1, omega 2, around. And when we will be doing our mathematical modeling, we will always stay in the rotating frame, but when we are returning back to description of experiment, very often we need to return to the Schrödinger picture and come back to the very quick accumulation of phase. Right now, we are using the delta, the detuning offset between the exciting central frequency and the frequency of the system. But we may need to return back. And here, if we do return back, then we can consider the following experiment. Systems of type 1 and type 2 are excited by pi over 2 pulses. Let's start from here. North. Pi over 2. Pi over 2. And then external perturbation stops. The system is allowed to evolve in time as it wants. The pulse is selected to be very, very short pulse, so that by the uncertainty principle, short pulse would cover broad spectrum. So we would say several frequencies. And then when one measures the magnetization coming from adding together individual contributions from each system, one will see that the total magnetization, let's say in X, will be a summation of frequency omega 1 and frequency omega 2. For two frequencies, it is typically seen as beats. And in addition, this is multiplied by envelope of relaxation with 1 over T2, which we will introduce and discuss in details soon. So this time dependence can be Fourier transformed, and then one would extract the frequencies. So if one would do this this function of omega, then it will have peaks at omega 1 and omega 2 with the width determined by this 1 over T2. And from this experimental, from pulsed nuclear magnetic resonance with the FID, free induction decay, so the external pulse induces these oscillations of polarization, and they are freely decayed. But there are components of oscillation with different frequencies. And these frequencies is what is needed to make identification of the chemical samples. Am I lying, or it is somewhat related to the truth?
Exactly my understanding.
I read it last night in Wikipedia. Okay, so the community represented by you guys doesn't object that it is correct. Now we are going back from the connection to experiment back to mathematical model. So what is the reason why these oscillations decay? What is the origin of this 1 over T2 dephasing? Why the lengths, if you look on this phenomena only for one system, it would correspond that the length of this vector decreases. So from now on, I'm forgetting about real experiments with several frequencies and focus only on samples with one frequency, one two-level system, which is either spin or like homologue transition molecule. But we will take into account that there are several interactions, that it is not isolated. And we will make an effort to find atomistic reasons to identify values of T2 and T1. T2 is a little dephasing a little easier, and we will be able to complete it in hopefully in 10 minutes. And T1 is extremely challenging, and one may need like a couple of weeks, or just to declare it and postpone it for whatever. Any questions or objections about this comment? Is it more or less reasonable? Okay. I accepted this head nodding as an accepting sign. So I'm reading this panel, and then we'll try to do more mathematical arguments in the same language. So there are two different principles for transversal and longitudinal time calculation for atomistic modeling. So for dephasing, transverse decay longitudinal. For dephasing, one needs to take into account that we do have driving force that make them to excite, and then we have an ensemble of very similar copies, very similar replicas of our model, but they are slightly different by the value of their splitting of the energy. And then the resulting signal is a summation of the contribution of all of them, average over an ensemble. If you carefully do it, there is a way to roughly estimate this 1 over T2. If you want depopulation, one needs to look from the different angle. One may still consider that we have one system, but it is not isolated, but it has surrounded, it is coupled to different degrees of freedom, which can be like rotations, vibrations of solvent, substrate, of whatever is around this degree of freedom, or maybe different degrees of freedom in the same molecule, or energy can be dissipated too. And here we make an average over ensemble of our primary system, and here we need to make an average over ensemble of the surrounding molecules for one system. This is a matter of like 10-5 minutes. This is a matter of several hours. Well, if doing the details. So we want to live an easy life, at least today, therefore we will focus on this one. Erase, right? So, what do? We redraw the same picture showing that we have number 1, number 2, number 3, number 4, of large number, and each of them is characterized by the offset. Here is plus, 3, here is delta 4. So we characterize our systems in an ensemble by their offset from the primary frequency. So you can consider that we do have an ensemble given this offset from minus d capital plus to plus d capital, maybe over 2. So it is like continuous band of all possible frequencies of this two-level system. On another hand, we know that if we are looking for projections, this Sx and Sy, that stand for magnetization, for polarization, then they appear as the linear superposition of the off-diagonal elements, bless it isn't high, of the off-diagonal elements of density matrix. Right? Such definition. And minus with 2i for Sy. So we may want to consider time evolution of the rho 1, 2 as function of t, but take into account an average over an ensemble. Yes? So in average, do it last 20 seconds. In abscess, do it last 5 seconds. In absence of ensemble for isolated system, the off-diagonal elements of density matrix evolve as accumulation of a phase, right? Just based on the equation of motion that we wrote down there. So if we set up Rabi frequency equals 0, meaning no field, we still stay in the rotating phase, then we will accumulate this offset value that will bring this exponential phase to initial value at time 0. Now we are committing average over ensemble, which means that we will be talking about rho 1, 2 is bar of t, which means summation of I of 0 and the time evolution. So we will add together. We will write this one once again. Summation I rho 1, 2 of t for a replica number I for each element of an ensemble. It is very simple, but I better pronounce it. F each element of ensemble. And we may want to normalize. We can assume that initial values are the same, but the difference will be in the pace at which the, let's use the letter J here, at which the phase is accumulated. So this delta symbol will be different for each member of an ensemble. It will be very similar, but slightly different. Frequency will be different. And instead of this summation with normalization, we can put rho 1, 2 out of brackets. It would be a good approximation to assume that they are the same. And then replace summation and normalization into integral from minus d capital over 2 to d capital over 2 e I delta h bar t. Integration over delta. Okay?
But isn't rho 1, 2 is
We can, it is a very
it's
good
outside the sum.
Yes.
Rho. Okay.
We can put it outside of sum without sacrificing any physical meaning. So now the only mathematical operation is to perform this integral. We have already committed this integral in the past when we were considering time-dependent perturbation theory, but there you were performing integration over time. Now it is the same stuff mathematically, but we integrate over energy, over frequency. Just to have simpler variables. So we are looking for rho with bar, which stands for average or ensemble. 0 times integral t d So in order to make simple integration, we bring I and t under sign of the integral, and we divide everything by I and t, right? It is how we typically take integrals. 1, 2, 0. 1 over t. And then the integral of exponential over the same integration variable will be the same exponential. So e to the I delta h bar t taken in the limits from minus d capital over 2 to plus d capital over 2. T plus bar, 1t times 0 plus bar, 1 over it exponential of I d over 2 times time minus e times minus I d over 2 times time. Right? Two t into 0. So we can divide and multiply by 2 and then identify the difference of imaginary exponentials over 2i as a sine function, right? So we have 2 over t times sine of dt over 2. We are almost done with our mathematical exercise. If we plot this row 1, 2 bar as function of t, it will start with its value of time 0, and then it will show this SINC function, sine divided by argument. So sine t divided by t. We do not care what happens for t less than 0, but for t bigger than 0, it will go this way. Right? Sine is oscillating, but 1 over t gives relaxation. And the instant of time when it will be for the first time completely 0, well, we can define half width or whatever, but this is just easier to find. So this point where element of density matrix will become 0 can be formulated as sine is equals 0 when argument is equal pi. So dt over 2 equals pi. Right? No objection. We need this function to be 0. We just want an equation for the point when it is small. So dt equals pi, then the solution t equals 2 pi over d. So what is d? D, Jabit, what is d?
That on this.
How can we refer to it by a single word? Distribution, disorder, something like this.
Deviation.
Deviation.
Standard.
Something that starts with D. I like the word disorder, but maybe it is not the best one.
Fluctuation.
Difference.
So the width of the distribution of frequencies. Width of the distribution of frequencies. And when we take, if we weight T2 equals to this 2 pi over d, then our rho 1, 2 element of density matrix will become 0, and projections S sub x and S sub y will also become 0. So this will happen because of the destructive interference of several systems, because they evolve in time with different frequencies. So this destructive, they will come to our time of measurement with different phases. But overall, average system is losing phase. Therefore, one can call it dephasing. Loss of phase. So T2 equals 2D over D capital, and then 1 over T2 is just D capital divided by 2 pi, where D is width of this distribution. bit of distribution of frequencies. Distribution of frequencies. Okay. If you need to go to another class,
We'll cancel today.
okay, then you can keep sitting here. But this was the main part of our meeting. Now we can talk more and draw more pictures just for illustration. Let's see if we need the density matrix equation of motion or Bloch equation. Probably not. And if I forget, you'll remind me. You were taking notes, right? Did you? I'll better take a screenshot myself. I just
Oh,
didn't.
you don't have your cheat sheet today.
Well, I'm preparing less and less, and if you come to extreme when I'm completely unprepared, then we will do it easy.
So hopefully you're never not prepared.
I hope so too. You can stay near the board
Oh, no, that looked like I did it.
and point something.
I can't take credit for that.
Why not?
I can only take credit for the Pauli equations.
You already took credit for Pauli matrices,
Yeah.
so you're already on the track. So I'll erase equations and then you'll draw some pictures. How far are we in this plan? We are done with nuclear magnetic resonance, Fourier distribution, integrate, yes, sinc function. And now we may recall that one always need to return into from rotating frame to Schrödinger picture. So we assume that pi pulse created a state on the equator of the Bloch sphere, right? This would be one, this will be two, and those will be superposition. Then I do not have enough steam and energy to draw 20 spheres at once, but I can draw several vectors. So if they accumulate I delta t phase, it means that it will change the angle appropriately. So angle proportional to I times delta times t. If it is negative, it will accumulate phase in the opposite direction. Minus I times delta times t. Right? And if you do have several such vectors, if you have not vectors, if you have average over ensemble, if you have a lot of two-level systems, each of which having different value of the delta offset, then we can draw many vectors, each of which going away from the original point. Some of them going left, some of them going right. And if we wait long enough, they will penetrate around the circle, populate the whole disk, and if one makes an average, add together all these vectors, they will add to zero. Like add together vectors of the opposite direction, results in zero. Add together vectors of opposite direction. Then upon average, the polarization, the magnetization of the overall system will become zero. Magnetization, proportional to summation over all vectors, will go to zero. So we can call it as free induction decay. Good? Nothing will change if this disk, did you play vinyl discs for music? Right? So if you have all this evolution, all these vectors, but we draw on a vinyl disc and let it rotate. The principle that opposite directions will cancel doesn't change. So there is a distribution of vectors and they all are quickly rotating. But the summation will be zero anyway, even if we multiply each element by e to the power minus I omega capital T, or omega is the leading frequency. Good? So we give a comment about the return to Schrödinger picture. Now I'm going to show a couple of images on the screen that will briefly remind what we were practicing in the enough. So what we were modeling in the lab last night. So if we tailor a pulse of such pulse area that it will correspond to pi pulse. So specific area that would lead ground state to lose its occupation from 1 to 0 and occupation of the excited state move from get from 0 to completely 1, then the off-diagonal elements of the imaginary parts of off-diagonal elements of the density matrix will temporarily raise during the pulse and then decrease to 0. If you repeat the same modeling, so we were propagating in time Liouville equation of motion for density matrix with time-dependent electric perturbation. If we shorten the pulse twice, or if we move the intensity twice as less, then the population of ground state will decrease only 50%, population of the excited will increase only 50%, and the off-diagonal elements, imaginary parts, will stop changing in the middle and will be non-zero. So this would correspond to moving of our explorer from the North Pole to equatorial line, pi over 2 pulse. Okay? And when one of this, and if we repeat the same simulation for slightly different distribution of frequencies, then it will be almost no effect to population for rho 1, 1 and rho 2, 2, but the off-diagonal elements, instead of being unchanged, they will start slowly oscillate, each of which with different pace. Will decrease and increase, and if we integrate over all these representatives of an ensemble, what we just did in here on the board, then we will get this thick dashed lines, and we see that it goes midway between this swirl of trajectories. And at a specific time, it will reach value 0. Then, because of this equally spaced distribution is too much of approximation, it will oscillate, but it will not come back. It is relaxing, and it means that the off-diagonal elements of density matrix disappear. System in average is losing phase, so that we call it dephasing. And the time when it gets to 0 will be just 2 pi over d capital, over how broad the distribution of these frequencies is. Good? Now, there is one more picture that I wanted to show that we actually did in the lab, but let me illustrate it first by a cartoon on the board. So it is the biggest challenge for my drawing skills. Suppose that we have a stadium, Coliseum, in ancient Rome. And today we are we are watching the race. Not of horses, race of humans. So there is a starting. And if you like the picture, the credit is not to me. I'm just reproducing from sources. So we have a starting point. And there are one, two, they all want to go forward. And there is a coach with a gun or revolver. So the coach gives a command: start, set, go. The sportsmen start to circle around the stadium. Suppose this one goes so far, this one goes maybe further away, and this one goes just a little. So as time passes, well, distribution of speeds.
No, I'm just laughing because the guys in the center goes to the least amount of space.
So there is a distribution of paces, and as longer we wait, as further away they will be along this track. So if we want to find who is quicker, we can easily do it. And the longer they run, the broader the difference between first and last is. If you have, instead of 3, if you have like 10 or 1,000, then at a given amount of time, they will distribute equally along this circular stadium, right? And if we make a vector from a center to each of the sportsmen, then the average of the vectors for all sportsmen will become 0, right? So it is an illustration of the free induction decay. each sportsman is a representative of one two-level system in the ensemble. The stadium is the equatorial motion on the Bloch sphere. So after a given amount of time that we just found out analytically distribution of their speeds, there will be no phase in this competition. Everything homogeneously distributed. But let's assume that the coach has a big authority and he may shut the gun for the second time, telling everyone must turn around 180 degrees and keep running. Turn around and run again. What would happen?
Disordered phase would rephase.
Yes, the quickest one will start going backwards and will arrive to the starting position at the same time it took him to depart from there. The slowest one will return backwards, assuming that they're not getting tired and they keep running at the same speed. So I'm just turn around. So if you wait equal amount of time, so time from start, time of second shot from the revolver, and time when all arrive back. You can set this time equal 0, this time equals tau, and if they running at the same pace, then time equals 2 tau, right? So if you make an analogy with Bloch sphere, when they all will come back, the adding together these vectors will be a constructive interference, and the value of the polarization of the magnetization will achieve largest possible value. Same at the initial time. This is possible. The question is only how to implement the coach with a revolver in quantum chemistry. How to make them to run in the opposite direction.
Didn't we do this yesterday?
We did, but can you verbalize what have we done?
So the first shot is a half a pi pulse, which then induces them to start doing that. And then you do a full pi pulse, which flips it, and then you should get back to the initial point.
Okay, so there are two ways to do it. First, one can just swap the sign of magnetic field, so that if they're getting inverse of their frequencies. And second, indeed, one can do a pi pulse, which means that everyone will be transferred across the globe on the opposite side, and then it will be a mirror image of the distribution. Meaning whoever was first will be last, whoever was last will be first. So it will be corresponding to motion in the opposite direction. And we indeed made this little experiment, numerical experiment yesterday. And it is what you guys got in your modeling, right? So here I'm not showing this swerves, otherwise it will be too busy. It is only length of the Bloch vector upon average and length of the transversal components, only x and y, without z as function of time. So the red is overall length, which is squared. It will be h bar squared divided by 4. So here is 0.25. And here the dashed line is the component contributed from the transversals Sx and Sy. So when we irradiate each of the system in the ensemble with pi over 2, then the maximal length is contributed only by Sx and Sy. So Sz will be 0. We will be on the equatorial plane. Sz projection is 0, but Sx square plus Sy square is maximum. And as time passes by, we are losing the length of this vector because of the dephasing procedure, dephasing effect. Right? But then, at a specific time, we are submitting the second phase, and then the evolution inverses. It's same as we suddenly flip direction of time. So it is mirror symmetric compared to this point, and it starts raising backwards. So the interpretation of this phenomena is that when the magnetization or when the polarization of a system is maximal, it has the highest probability to interact with this perturbing electromagnetic field. So this probability is so high that the ensemble of systems will interact even with the zero oscillations of electromagnetic field. There is a chance of spontaneous emission if we are talking about optical implementation of this phenomenon. So several molecules, all of them come into the same value of the transition dipole moment expectation value, which means the system is really strongly polarized. It's such big polarization that it will interact with a mode of electromagnetic field and emit light. So if you're talking about photons, electromagnetic light, it means that we irradiate system with pi over 2 pulse, irradiate second, and then we wait equal amount of time, and then it flashes back. So it spontaneously emits light, but not randomly, as one observes in like time-resolved photoluminescence. When one system in an ensemble randomly emitted this time, another at this time, here they all would emit at a specific time. So it's like nothing, 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 and then big glowing with a very short pulse. The duration is the broadness of this pulse corresponds to the dephasing time, but it is still very short event in time. And an analog of this photon echo is also available in nuclear magnetic resonance, and then it is referred to as spin echo.
So after it emits the light, does the dotted line go back to 0 and stay at 0, or does
Yes,
it
yes.
past that again?
No, in our modeling, we have the small oscillations. But if one has dense distribution, it goes to 0. Well, if you send more than 2 pulses, there are more exotic techniques like 3-pulse photon echo, wave packet interferometry. And I think one of you has volunteered to mention something about it. I don't remember who right now, but it is. Let's see how far we are in our list of subjects. So spin echo, photon echo, cartoon of a coach with gun, and I think we are done for today. So, thank you for investing your time. Meeting number 20 is dismissed, and looking forward to see you in 2 weeks for listening your presentations.
We'll meet next week.
No meeting next week.